Alright, so the purpose of this video is to take a look at the neural network that I wrote for you from scratch. I'll say that again. Okay, so this is following page 154 of the notes directly. So if you don't have those open, go ahead and open those up. Um, yeah, it's the simple construction of a feed-forward neural net. And so we're going to do this using linear algebra. And so let's go through the form here. So notice that I'm writing this actually as a function, and the reason I chose to write this as a function is so that I could put the subroutines down here at the end. We can open those up. Activate, the derivative of the activate function. I should have picked a better name for that. This is the confusion matrix. It looks like Matlab, so I'm using Matlab's editor here, and it looks like it's wanting to put a, okay, it's summarizing information for me. I haven't had to do that before. This is a new editor here. Nice. Okay. Um, so these are all the helper functions. So down here is the train test split that we wrote for Matlab. So I just copy and pasted these down here, so I wouldn't have to have a bunch of files beyond this main. So the only file you need here is main. Okay. I better put these things in here so you can see what's going on here. I don't want to hide anything. Okay, so I guess that's being hidden too. Okay, there we go. Now we can start. Okay, so you see the only thing I need is the iris data 2, and this is the iris data, so you can imagine we're just doing a classification problem. And so this is also showing you how to do the scaling. So we'll go ahead and do the standard scalar of our matrix X, and the iris data is 4-dimensional. Okay, so that puts it out into XS, and then we split it into training and testing. And so we'll build our neural net with the training set, and then we'll test it with the test set. And I usually use a 70-30 split, like usual. It's a pretty good number. The alpha I'm setting, this is my learning rate for the stochastic gradient descent, is 0.1. The number of epochs, however you want to pronounce that, is 800. This is, remember, the number of times that you go through the data. By the way, the training data is randomized here when it comes out of train test split, so you don't have to worry about randomizing it in the loop. If you did not do this step in step line 11, you may have to randomize your data, because the order of the data can really mess up your training if it's not random. Okay, let's see. And so then I just pick up some sizes of things or shapes just to get the neural network set up. And in this case, line 21, I'm defining a network with 10 nodes in the hidden layer. That's probably overkill, but I want to be sure I'm getting a nice cluster, or a nice output for you. Okay, so now what am I defining? These are all the structures of the neural net. I've got my pre-state for layers 1 and 2, the states for 1 and 2, the derivatives of the states for 1 and 2, and the deltas for the 1 and 2. Now really you don't have to predefine all these structures. I'm doing it just so you remember what the dimensions of everything is. And so the parameters are really W1 and W2. Those really do need to be there. And then same thing with the B1 and the B2. And I'm initializing everything to be random. And so the random that I'm using is the normally distributed random numbers, which means that they could be positive and negative, but they do have zero mean and unit standard deviation. I'm just picking uniformly random so I get some negative numbers as well as positive. Good. And then this error here is just measuring, or it's going to keep track of the error as I go along. Good. And so we're just going to loop through the number of epochs, set the error to 0. Now this is being set to 0 here because it's going to be keeping track. It's going to be adding the error for every data point. And so at the end, error j is going to be the sum of the errors of all of the data squared. Okay. And so the forward pass is done first. We just define our pre-state. Can anybody see that? We do the pre-state, state, and then I also store the derivative of the state. That's it. That's layer 1. Go to layer 2, pre-state, state. Sorry about that. I shouldn't be doing that, I guess. And then the derivative of the state. There's layer 2, done. Backwards pass. Now I'm going to fill in my deltas. And at the output, the deltas are t minus y. So that's the t minus the y. Right? Remember, it's the training set that we're working with here. Okay, and then the delta on the middle layer was defined in our notes. So I'm just writing that as our matrix form. And now we just update the weights and the biases, just like the formulas that are in the notes. So dw1 is the well, instead of the state is the x value, right, for layer 0. And so that's why you're seeing the data coming in here. X train is the state on layer 0. Okay, I didn't want to put I can't index 0 in Matlab, so okay. That's only a Python thing. And so then I do the change in the bias as well, and then I make the change in the second weight matrix, just as we defined in the notes, and the second bias term there. And then we update our weights and our biases, and we compute the error, and we're done. Wow, that's fast. So this is a neural net. It doesn't really look like a neural net, because all you have here are a bunch of matrices and vectors. But that's really what a neural network is. It's just a function going through the layers. Good. And so the rest of this stuff is really just outputting or translating the output into something that the confusion matrix can read. And so line 57, I'm making a note here. I'm actually looking at the error on the training set, and the only reason I'm doing that is to make sure that we're getting good training on the training set. Because if you don't have a good error on the training set, that may mean that there's something wrong with your algorithm. And since we're constructing our algorithm ourselves, we're just doing this as a check. If the error was getting really big on the training set, we would be in trouble. And so the line 64 through 69 are where we actually compute our real estimate of the error using the test set. Okay. And so notice what I'm doing here in Z out in line 65. I'm just feeding X test through the data. So W1 times the X test plus B1, that's the pre-state. I activate that, and then I apply W2 plus B2 to that, and I'm done. That is the output. And so remember what's happening here again. This is converting the vector that's in our how many different classes do we have? 3 different classes of flowers. And so t-test is a vector in R3 telling us which class we are in. And so z out is also going to be a vector in R3. And so the maximum element there is telling us which class the flower is in. Okay, so that's coming out in T1. And then the maximum element in t-test is coming out in T2. And so T1 and T2 are the scalar numbers, right? The real numbers, or the integers that represent the 3 classes. And those are the vectors that I want to put into the confusion matrix. So the confusion matrix isn't going to understand what you're trying to do if you try to put matrices in there. The arguments for the confusion matrix are 2 vectors of integers where the classes are given to you there. Okay, good. And then I just, this bottom part is just to save the network that you've just trained. So that's going to be the output. So when I want to train this, I'll just say net equals main, and I'm done. All right. Do you think it's going to run? Well, let's give it a try. I've got my Matlab file right here. So this is the real Matlab. Let's see if it'll train in the real Matlab first. I'll just say net equals main. Done. Woohoo! Look at that beautiful training. That looks nice. And notice that the output here is telling me what everything is. So if I want to go back and look at the weights and biases, I can do that. Otherwise, they're right here. So notice that the W's, there's 2 arrays here for the weights and 2 arrays for the biases. And then I've also put out the training and testing data. So we could also plot the error if we want. Oops, that's net.error. And there it is. Look at that beautiful training. So we got, so it did a really good job initially, and then it's trying to get even better and better as we go along. Very good. Do you think it's going to work in Octave? Let me pause for a minute and give it a try. Okay, so I've got things loaded up in Octave here, and so just on the right side here you can see in order to run this we'll need the iris data2 data file and then our main.m, and we'll just go over to the Octave command window here and see what happens. We'll just run it just like we did before. If I can get that to stop, there we go. And then we'll just type in net equals main. Oop, I better be ready. I think we'll need to put extra time. Add 15 seconds. I'm going through the data 800 times, so. But there's not that much data, so it shouldn't take that much time. Octave Online, though, is slow, I guess. Add 15 seconds. Oh, there we go. Very good. And yeah, I didn't get all that output before. Oh, it's putting out the entire network structure, I guess. That was kind of a pain. Okay, where's our? I'm trying to find our. There they are. Ooh, look at that! Beautiful, beautiful confusion matrix. Okay, so it does run in Octave. The next video will do the same thing, but we'll go through it in Python. So you don't need to see that unless you're running the Python and curious about it. I'll see you later.